Hello friends, welcome to the part 7 of my Arduino Quadcopter project. In today's video, I will be explaining the code, that is program, that I have implemented to get a fast and efficient response and a serial communication between the Arduino Nano and the GPS module. So let's get started.
Okay, here's the code which I have written to acquire data from the GPS module, that is a Neo 6M module. So I would like to begin with the comments section. So you can see I have mentioned that disabled all enemy sentences and GPS sending only GPLL sentence. So I am only receiving one sentence from the GPS module. I hope you are aware that Neo 6M GPS module uses the serial protocol to transfer data to the microcontroller. That is, it transfers over the UART. So this data is transferred in the form of lines or NMEA sentences. NMEA sentences. This is a global standard which all GPS modules follow. And now what I want to tell you is that I have disabled all the other sentences which are being transmitted by the module, and I have only left the GPLL sentence. The GPLL sentence contains the latitude and longitude information only, and I'm only concerned with this. So I have done this to increase the response of my controller, and I have eliminated all other data which is not of very high importance right now. Okay, I'll take you to the website where you can see. I'll just quickly go through the various sentences and what is the purpose of GPLL, just to make things clear for all of you. Okay, here I'm in this website called the aprs.nl. There are many other sites websites where you can find description of the various enemy sentences. So here you can see we have this $GPBOD. So these are the these are the NMEA sentences. They all start with the dollar symbol, and the second character is a G and the third character is a P, and the remaining last three characters will specify what data is contained. For example, GPGGA. GGA contains the global positioning fixed system fixed data, basically the time and the number of satellites used to acquire the fix by the module. So similarly we have GPLL. So this GPLL is the sentence which we are retaining or which we are acquiring from our module. So you can see this contains the latitude and longitude only. Okay, by default a Neo 6M module will transmit some 6 to 5 sentences, 5-6 sentences, which contains GPGGA, GPGLL, GSA, GSV, and RMC. So all of this data is actually not required, and not required as in the Arduino is not capable of receiving that many data and also maintaining a proper loop timing, that is a cycle. I want to reduce it, so I have removed those sentences. I will not go into detail. So let's go to what GPGLL contains. So here we have a description. If you click on that, it brings us to this paragraph here. You can see example 2, because example 2 is the format which I am receiving from my Neo 6M. Okay, so you can see yes, $GP GPGLL, then we have the latitude, it is north, and then we have the longitude, which is west. Then this is the UTC, that is the time at which the fix was taken. So it is basically 22:54 seconds and 22 hours 54 minutes 44 seconds UTC. Finally, this A is the most important character for us. This A, whenever it is available, it means that the data we have received is valid. We have received valid longitude and latitude data. So I will explain that I am using this character to identify a valid GPS fix. Let's get further into our code. So I'm not using a GPS library, that is a popular tiny GPS plus library. I'm not using that because I could not get a sufficient response from the library. Since we are applying our GPS to our drone, so we need a very good response time. So that is what I was not able to achieve. So I discarded the use of this. and I am using the basic algorithm, that is I have written the code which is originally based on Joop Brookings YMFC STM32 Quadcopter. The links of that website in my video description. So I have taken the algorithm from there. So if you can see here the code, so what I'm doing is my code is parsing through the serial data, or it is extracting the characters from the NMEA sentence GPGLL, the latitude and longitude information. Okay, so I am not using a library, I am parsing through the serial data. So there are no other libraries, only software serial. Okay, then we have the software serial defined RX, TX, pin 3 and 4. The default baud rate of the GPS serial is 9600, which we are using, and there are some variables defined. This is a default. I have just kept the default latitude and longitude. You cannot see the decimal points here because we are treating this values as integer, which is easier to work with, and these are all converted to degrees. So we will have a decimal point somewhere here. The actual value 22 degrees, 0.18278000 degree, not minutes. It should be noted. Similarly for a longitude, I'm using GPS and the proportional and derivative gain of 2.7 and 6.5. This is default, taken directly from Joop Brookings code. I haven't tested it yet. Maybe it will change. And there are other variables defined, not important right now. I want to show the flow of the code. Another important thing is the yaw angle of the drone is set to 0 because I'm not using a compass. I haven't implemented a compass yet, which is the next part of my project. So right now we have kept it as 0, which means my drone is oriented towards the north direction. The drone's front is oriented towards the north direction. The setup. This is the setup. Nothing much. Serial.begin 115-00 baud rate. This is the baud rate at which the laptop or my laptop will connect with the Arduino Nano. And then GPS serial.begin. This is the software serial. The baud rate is right now 9600. And then we go to the GPS setup. So this is an important part of the code. Let me take you there. So this is the GPS setup. So you can see I am starting the GPS serial with 9600 baud rate. Some delay is required, and then I have disabled GPGSV, one of the first sentences which is being disabled. Okay, then once this is disabled, I give a delay, and then I'm setting the refresh rate of the GPS at 5 Hz. By default, the Neo 6M module comes with a 1 Hz refresh rate, which is not sufficient for us. Once the refresh rate has been set, we are changing the baud rate to 57600 or 57 kilobits per second baud rate from 9600. So this is done. So this entire code is actually copied directly from Joop Brookings STM32 code. But after this is what I have added lines to my code. You can see this additional lines. So in these additional lines, I have disabled GPGGA. You can find out from the website what this means. And then I have also disabled GPVTG. Again, similarly GPRMC and GPGSA. So 1, 2, 3, 4 lines plus the additional first line. 5 lines have been disabled. So that way I am receiving only GLL. So the way we communicate with the GPS, or we instruct the GPS module, is by sending these characters or bytes over the serial terminal. So I have made this disable GPGGA is basically an array of integer, unsigned 8-bit integer or a byte. There are 16 such bytes, 16 bytes here, or 16 characters. And then I am doing a GPS serial.write. So this is the variable or the array, and this is a number of bytes that has to be sent, 16. Similarly for others. So this I found out from the various, I did a research and found out from various, basically from the Arduino forum. Thanks to the guys there, the registers which have to be set. So this is all about the setup. So once we are done with the setup, we can proceed to the main loop of the program. So in brief, I have changed the refresh rate of my GPS to 5 Hz. I have changed the baud rate to 57600 bits per second, and then I have disabled 5 additional NMEA sentences which is not required, leaving only one NMEA sentence. Okay, let's proceed to the next part of the program. So we enter the loop of the code. There is a void loop. We begin with the GPS PID function. So the ultimate objective of this code will be to provide us a GPS hold. It is enable the drone to get into a GPS hold mode. So for which we will require a PID controller. Okay, we will go to the GPS underscore PID function. So this is the GPS underscore PID function. So as you can see, the first thing that is done here is we are calling the read underscore lat long function. So this function is nothing, it just acquires the lat and long coordinates. This will fetch the lat and long coordinates. Okay, we will go to this. Let's go to this function. I'll show you that. So this is a function here. Okay, it's not very, looks long, but it's not complicated. So I'm calling loop timer. This is nothing but just to see the execution time. Not used during, will not be used during the actual functioning. So which we always start with GPS while GPS.serial is available. So my microcontroller will scan for any GPS data received, or sorry, any serial data received over the software serial terminal. Once it is received, we will save the information into a array, read serial byte, a variable, which is basically a character variable, character type variable. So then we will see whether that first byte, the byte that we have received, is a symbol or a character $. As I have explained that the presence of a $, identifies that a new NMEA sentence has been received over the serial terminal. So this indicates that we have received a new NMEA sentence. So then we are beginning. Once we have received this, we go into a loop, and then we have a buffer. We have a buffer called the incoming message buffer. It is an array of characters. Size of this is around 50 size array, because I will be receiving some 49 or 45 characters from the serial. So once we receive the first character, the entire buffer is set to a character -. So basically we are flushing the entire memory or the buffer. Then comes the important part. So now we will scan for these characters L, and this A. So you can see I have written if incoming message at the location of the array 4, the fourth location of the array is equal to L, and the fifth location character is also equal to L, and the 44th character is also equal to A. So that means we have received a GPL received and a valid data has been received. I have explained that the A means it means that a valid GPS data has been received. So this sentence will ensure that we have received the new GPS coordinates.
So let me show you the structure of the data packet.
Okay, on the screen you can see the structure of the serial information or the NMEA sentence that we are receiving. So it will always start with this dollar here, GPGLL. So I am receiving only this sentence. So then we have this then the latitude information 2218.27782. The next character is the N, which stands for north, and after this we are followed with the longitude information, which is 8717.74261 E. Now it is important to note that this information is actually stored in this manner: 22 degrees, 22.18 degrees, and then the remaining data after the point is in minutes and seconds. Similarly for the longitude. So this information we will convert to a usable form for our microcontroller. And after that we have the UTC 085340.20. This stands for the UTC, universally coordinate time. It is the time at which the fix was obtained. And the 44 character, you can see I have numbered all the characters here. These blue color numbers are the number of the character in the array. That is the incoming byte array which I just showed you. So the dollar symbol stands in the zeroth array location. G stands in the 1. So we had checked for the we had checked for the incoming byte location 4, incoming byte location 5 for these characters L and L, and the 44th location for this character A. So if these three characters are found, means we have a GPS coordinated. We have received a GPS latitude and longitude coordinates. So this is how we are parsing. The term is called parsing the data. Our incoming byte will store this entire data, and each of these characters are stored in each of the array's location. So we have 49 characters for this GPGLL sentence. Okay, I'll get back to the code now and we can continue onwards. Okay, I was explaining this in the image, the showing the structure of the NME sentence or the data packet we are receiving in the serial terminal. So once I told you that once this information is true, that means we have received the new coordinates. Once we have received the coordinate, now I will start extracting the latitude and longitude information. So you can see here my latitude and latitude. The first character of my latitude starts with the buffer location of 7 and then 8. 7 and 8. These characters 7 and the characters 8 are the it was 22 degrees. So they are degrees. Okay. This is the information in degrees, and then the other locations are 9, 10 up to 16. So we have done a conversion here. We have converted all the data into integer, remove the decimal point, and then we are doing a division by 6 to convert the degrees, the minutes to degrees. Just a side note, this part is actually taken. This part is taken from Joop Brookings code as well. Only that the condition here I have changed this condition. I have redefined this condition to suit my need. Okay. So this credit goes to Joop Brookings. Okay, finally we're dividing by 10. It is we are getting a format. We are removing the last decimal point, I think, in this. So similarly we are doing the same for our longitude data. The longitude data starts with the character 20. It is 87. Okay, sorry. The longitude data has 3 digits assigned for the degree, because longitude information varies between plus 180 degree to minus 180 degree, whereas a latitude information sticks between 90 degree and minus 90 degree. So we need 3 characters for the longitude. In case our drone flies off to a coordinate or a longitude which has a 3-digit degree, say a 120 degree or 130 degree, so we have 3 digits assigned for that, 3 characters I must say. So it starts with 20, which is 0 in my case because my longitude is 87 degrees. So the first character will be 0. And then the remaining minutes data, same, is being converted to degrees. So we have the latitude and longitude information. Then comes the other information, such as whether we are in the northern hemisphere or the southern hemisphere, or we are in the eastern part of the world or the western part of the world. Right now I am in north, my location is northeast. So this is a variable which stores this information. If incoming message 18, so the 18 character contains this information, north. Similarly 32nd character will contain the east or west information. Then we are doing here is, if this is the first time the loop is running, that is the first time we are getting the GPS data after the drone has been powered, all the GPS previous data will be set to the actual data, the current data. Else, if this is not the first time, the GPS previous data, the current data is assigned to the previous data. So this way we are okay, and we are also setting this flag. There is a new GPS data available flag I have kept. It is a boolean flag. So if the moment we have received the new data, it is set to true. It is set to true. So that's all for the function read latitude and longitude. The sole purpose is to get the latitude and longitude and highlight whether we have actually some new data or not by using the flag which I just showed you. Okay, we are back to our original function. There is a GPS PID which we are calling in the loop. Our primary loop calls this function. Okay, in the loop function we are calling GPS PID. In turn, GPS PID calls this read latitude and longitude, which I have already explained. Now it does this part of the function, and actually we'll see whether the flag, it is a GPS data availability flag, is true or false. If it is true, means we have received a new set of GPS data, and then it goes into this loop, into this part of the loop. We are calculating the GPS let error, the GPS long error. So based on the latitude GPS desired. So this desired latitude will come from my what you call the remote transmitter, or maybe I can define waypoints, predefined waypoints. Right now I have just kept it fixed to some predefined value. So once the error is acquired, then we are calculating the correction in the ESC pulses required to correct the GPS coordinates. That is, and how do we do that? We do that by changing the pitch angle or the roll angle of the drone. So if you change the pitch angle, which is basically the pitching of the drone, in my case, since yaw angle is 0, so the drone is aligned with the north-south axis. So pitching forward means I will go towards the north, and pitching in the reverse direction means I'll go towards the south. So this part of the code generates the pulse which will be added to the ESC pulses. Okay, so nothing much here actually. So just that we have a P and D controller. Okay, so this is a GPS P gain, and this is a GPS D gain. We are using a P and D controller. So the first part, that is a P gain, will just be multiplied with the error, which is proportional, and the second part, D gain, will be multiplied with the difference in the error, that is the previous error subtracted from the current error. So in a way, this is basically the velocity, the drone's velocity. We are actually dealing with the velocity of the drone. In other words, it's also called the damping. It acts like a damping, an artificial damping to the drone, so that our drone does not overshoot the desired coordinates. And then I had mentioned you that the north and south direction. So the GPS coordinates are actually in the form that if in the northern and eastern, there is a northern latitude and the eastern longitude, they are positive. They are positive 22 or positive 87. But if they come to the southern hemisphere or the western hemisphere, then this we have a minus sign in front of the latitude and longitude. Okay. So that is what we are doing here. If the latitude is north, then the pitch correction becomes negative. Oh, sorry, if the latitude is not equal to north, that is it is south, then the pitch correction becomes negative. Similarly for the longitude. And then we have the GPS roll adjust or the pitch adjust. Now this is nothing but we are doing the correction here. It is the sign correction. This sign correction is being added to the pitch we just calculated. This pitch we just calculated, and in this we are also multiplying the yawing of the drone or the yaw angle of the drone. So the GPS roll adjust north is the pitch adjustment, that is along the northern direction, along with the sign, whether it is south or north, contains the sign here. This again is multiplied by the cos of the yaw angle. Now you can do some research. So basically, when the drone is operating, it may be at some angle. The head of that is the front of the drone may be at some angle to the magnetic north of the earth. Say it is at 20 degrees or 30 degrees. So that angle is actually multiplied here. The cos of that angle is multiplied here. Okay. After that, we are performing a limit or setting boundaries to the pitch adjustment or the roll adjustment. That is 300. I'll have to tune this maybe, but this is to prevent the GPS PID controller from overtaking the entire control, so that the user does not have any control in that case. So this is a limit. Once this is done, we are just setting the latitude previous error to the current error. Similarly for the longitude error. This is a check here. If the time between each, so if the time exceeds 1 second, it is between two coordinates measurement, time exceeds 1 second, means we have lost our GPS fix. So it will set a flag, some error will be sent. Once this is done, we are setting the new GPS data available to false. So it means we have received the new GPS data, we have utilized it, and now we are waiting for the next set of data. Okay. So on the screen you can see this the data from the serial terminal. So you can see this. So I am printing the latitude and longitude information in degrees. With the decimal point removed. Okay. So here the decimal point will be after 22.3, and in this case the decimal point will be here after 87.2. So these are my latitude and longitude, and I can see that I am receiving data quite fast actually. It is 5 data per second, and each latitude and longitude read takes 10 milliseconds, 9.5 milliseconds to be precise. So with all the optimization that I have done, I could achieve read time of 9.5 milliseconds. Okay, so I have set some more serial data. I have increased the number of data that is being transmitted. So let me pause this. So if you can see here, so these are the 3 sets of data which I am transmitting. So latitude longitude information and the latitude and longitude error, that is the difference between desired and the current latitude longitude, and the corresponding PID pulse or the PD pulse, proportional and derivative pulse, calculated. So 207 minus the roll correction is minus 207 and the pitch correction is 464. So this actually the value is exceeded the threshold of 300. So I will set this to 300 in my code. It will never exceed 300. So that's it for the code. Okay, let me show you the hardware. Let me show you the hardware. So what you can see on the screen is the GPS. This is the GPS module, and you can see the LED blinking. This is a 1 Hertz blink, which means we have a data. Right now I am indoors, and today I am not facing any issue with the reception, satellite data reception. So this data I am receiving on my serial monitor at a 5 Hertz rate. Okay, there are many things I would like to discuss here, but I think that I will make that into a different video. So like I have explained, my flight controller, this is the flight controller which has the inertial measurement unit, and it operates at 5 Hertz, at 200 Hertz, and this is the secondary Arduino Nano which is acquiring data from the barometer BMP280 and the GPS module, and also I have this ultrasonic sensor underneath, if you can see that. Okay, so all these three sensors are being governed by this microcontroller. One important thing I like to finish this video is that Joop Brookings original YMFC 32 flight controller code is written for the STM32 microcontroller. So the algorithm which he has followed may not work on my Arduino. So my entire objective here is to implement the GPS module onto my Arduino board. So for that I have changed many of those things, like disabling many of the NMEA lines, and also the capabilities of Arduino is, I think, at its limit. Probably that is the reason why Joop Brookings must have switched to the STM32 microcontroller.
Okay guys, thank you so much. Thank you for watching the video. Do like and share, and do subscribe to my channel for more interesting videos. Have a nice day. Bye bye.